we now have a basic sense of how to compute some partial derivatives, and now we're ready to actually take a look at some more applications. We've been sprinkling these through the lesson so far. Now we're just going to focus on these, and we'll also describe how we can actually find these partial derivatives using technology, since partial derivatives aren't always nice and clean and easy to find. So I'll show you how to do that as well in an application called Wolfram Alpha, but there are many others that will do these as well. So let's start with our first problem. The number Z of research articles in Physical Review, so Z is the number of research articles that were written by researchers in the US from 93 to 2003, can be approximated by this function. And here we're told that that x is greater than or equal to 3,000 and y is, x and y are both between 3,000 and 6,000 articles each year, where x is the number of articles written by researchers in Europe and y is the number written by researchers in other countries, excluding Europe and the United States. So basically this is going to give us the output of this function will tell us the number of research articles in the US based upon how many articles were written in Europe and other countries excluding Europe and the United States. So basically if you tell me how many articles were published this year in Europe and other countries, then I can estimate, I can plug those numbers in and determine how many were produced in the US. So again, number of European articles, number of articles in other countries, and from that we can estimate the number of articles that will be written in the United States in that year. So we want to find these partial derivatives. And to find dz dx, we know that that means that we need to hold the other variable or variables constant. Now, if there were three variables, then we would do exactly the same thing, but we would hold everything but the one variable constant. In other words, we would treat all other variables besides x as being constant. So the derivative of a constant is 0. The derivative of negative 0.71x is negative 0.71. And remember, we're holding y constant, so that means that this term right here is a constant, and so that means its derivative will be 0. So we get this value, this constant value, negative 0.71. Now, and again, put that over 1 because that has units of change in z per change in x. So what does z represent? Well, it's the number of articles in the US. And what is x? Well, that's the change in the number of articles in Europe. So this might seem like a strange thing to try and interpret, but basically what we're saying here is that for every one additional article published in Europe, the US decreases publishing by, now that's approximately 0.71 articles. So I'll just say by approximately 0.7 articles. So in other words, as Europe continues to publish, the trend seems to be when Europe is publishing more, then the US is publishing less. So if we knew that this year Europe was going to increase their publishing by 100 articles, that would indicate that the US would be publishing 70 fewer articles. Now as we interpret dz dy, now we're holding x constant. So any terms that involve x are going to be treated as constants, namely this one here, negative 0.71 times a constant is a constant. So the derivative of the first two terms will be 0, and the derivative of 0.5y will be plus 0.05. And so we get 0.5 over 1. So once again, the output z is the change in articles in US. I'll just say articles in US to abbreviate it, per one article in other countries. I'll just say in other. So we could say similarly, for every one article published in other countries, excluding Europe, I'll just put other in quotes because that refers to excluding Europe and the United States, the US publishes 0.5 articles. So that's a constant rate of change. So every time we know that a country other than US or Europe publishes one article, then we're not publishing as fast. They're publishing twice as fast as we are. So another way to think about this ratio is this is instead of 0.5 to 1, we could think about this as a 1 to 2. So the US only publishes one article in the Physical Review for every 2 articles published in other countries. Now, if we want to begin to understand how this is all panning out geometrically, in other words, on the graph of the surface, how do we visualize these quantities? Well, here I have graphed the x and the y axes, and this vertical one is, of course, the z-axis. And if I were to isolate a point, let's say I isolate this point right here. And we've already established that for every 1 unit change in the x direction, in other words, in this direction, parallel to the x-axis, if I increase x by 1 unit, I will get a change in z of negative 0.71 units. And we can see that this plane is actually tilted in such a way to where if you were walking along this surface, you would be walking downhill as you'd be walking towards the right. And the fact that it's a constant negative 0.71 means it doesn't matter which point you pick. If you walk 1 unit in the direction of x, your change in z per change in x will always be negative 0.71. On the other hand, if at any point, regardless of which x and y we're at, because again, these dz, dy did not depend on the value of x or y, but if I move 1 unit in the y direction, if I move 1 unit this way, then my change in z, we can see we're now going uphill. The change in z per change in y will be 1/2 unit. So it's positive, means we have a positive slope. So this plane is kind of tilted upwards in this direction, but downwards in the x direction. And same thing up here. We could say the same thing. We could say that here the dz dy equals 0.5. Anywhere, in fact, the dz dy is 0.5. Now, it's not always the case that our function is linear as it was here. So in this next example, let's consider this. The fraction of Mazda car owners who chose another new Mazda can be modeled by the following function. So M represents the number of car owners or people who used to own Mazdas, who, when they bought their new car, they bought another Mazda, is dependent on the fraction of Chrysler car owners who remain loyal to Chrysler, and F is the fraction of Ford car owners remaining loyal to Ford. So basically, we want to know for every Chrysler owner who remains a Chrysler owner, and for every Ford owner who remains a Ford owner, how many Mazda owners will there be who remain Mazda owners? Let's take a look at an example. If, for example, we had evaluated M of, and I'm going to go ahead and reference this second problem here because I think it'll help us make more sense of what's going on. So part B, it says 1 year it was observed that C equals 0.56 and F equals 0.56. So that means 56% of Chrysler owners remained Chrysler owners that year. They bought another Chrysler. And 56% of Ford owners bought another Ford. according to the model, in that particular year, what percentage of Mazda owners remained loyal to Mazda. So we want to evaluate M of 0.56 and 0.56. And if we plug these values into here, and noting that all of these three variables, C, F, and M, are between 0 and 1, because you can't have more than 100% of Mazda owners who remain Mazda owners, but you can't have less than 0% of Mazda owners who remain Mazda owners. When we plug in 0.56 for both C and F, we get approximately 0.20. And what that allows us to say is, in that year in which 56% of Chrysler owners bought another Chrysler and 56% of Ford owners bought another Ford. So in that year, 56% of Chrysler owners remained Chrysler owners. 56% of Ford owners remained Ford owners. In that year, 20% of Mazda owners bought another Mazda. So we see that there were a lot of, in that year, Chrysler and Ford owners who remained Chrysler and Ford owners, but not very many Mazda owners bought another Mazda. About 1 out of every 5, in fact. And then the other 4 out of 5 must have bought another car. Now, it might make a little bit more sense to evaluate these partial derivatives. And in doing so, we're going to do this 2 ways. One is just algebraically, and then the other way, we'll show how to compute these with Wolfram alpha. So first, let's compute dm dc. And now we're going to take the derivative of each term, noting that any term in which there's an f, exclusively an f, those derivatives are going to be 0, because when we're taking the derivative with respect to c, we're holding f constant. So the derivative of 9.4 will be 0. The derivative of 7.8c will be 7.8. The derivative of 3.6c squared will be 2 times 3.6, 7.2. c to the first power. The derivative of this term will be 0. And now when we focus on this guy here, we're holding f constant, so I'm going to write this as negative 22f times c. And so we think about this as being constant because we're holding f constant. So we have a constant times a variable to the first power, which will give us a derivative that is just the constant. And then we'll have plus the derivative of something that depends only on f, which is 0. So if we simplify this a little bit, we get 7.2c minus 22f plus 7.8. Okay, now that obviously the value will depend on the current fraction of Chrysler people who are, we'll just say loyalists, Chrysler loyalists, and depends on the percentage of Ford loyalists. So we can say, however, that the units of this will be, this is the fraction of Mazda loyalists to every one, for every one fraction of Chrysler loyalists. Now, when we evaluate this at the point 0.7, 0.7, we get 7.2 times 0.7 minus 22 times 0.7 plus 7.8, and we get negative 2.56. So dm dc evaluated for the ordered pair 0.7, 0.7 equals negative 2.56 to 1. Now remember, this is a fraction, so we could think about these as percentages. So we could think about this as 256% to 100% if we converted those decimals to fractions. So what this means is that for every 100% increase in the fraction of Chrysler loyalists, there is a decrease of 256% in Mazda loyalists. Okay, so we might imagine this to mean that if you have a 100% increase, if the fraction of people who remain Chrysler loyalists doubles, then in that kind of year, we see a 256% decrease in the fraction of people who remain loyal to Mazda. So maybe part of that is because more people are becoming loyal to Chrysler, and so there's a big drop-off in the Mazda loyalty group. Now, if we take the partial derivative with respect to f holding c constant, now every term with c in it, this is a constant, this is a constant, this is a constant, those derivatives will be 0. The derivative with respect to x will be negative 38. The derivative of this, now we're thinking about negative 44c as being a constant times f to the first power. That will be negative 22c. And the derivative of 43f squared will be 2 times 43, which is 86f to the first power. So we have basically just these three terms here. And now if we evaluate dm df, at the ordered pair 0.7, 0.7, then we would take negative 38 minus 22 times 0.7 plus 86 times 0.7, and we get 6.8. 6.8 over 1, or since we're dealing with fractions here, it makes sense to describe this as a percentage change. And we would say something similar. We would say that for every 100% increase in Mazda owners, in Ford owners, there is a 680% increase in Mazda loyalists, right? So if the fraction of people who remain loyal to Ford increases by 100%, then Mazda loyalists tend to increase as well. Now, that's not because of the Ford. We're not saying it's a cause of the Ford ownership. It's just a co-variation, meaning as Ford ownership goes up, Mazda ownership goes up by almost 7 times that amount. Now, let's look at a graph of this, and we can kind of imagine that here is C and here is F over on this axis, and then this is our Mazda axis, this vertical one. So maybe I should say that this is the F axis, the green one. So at 0.7, which is roughly about here, 0.7, roughly about there, that at this point, right above on the surface, that if you move 1 unit in the C direction, you get a decrease in the fraction of Mazda loyalists. However, if we consider a change in the F direction, then we're actually traveling up that paraboloid. And I think it would be a little bit easier to visualize the fact that we're actually on this side, that we're not that were on this side of that paraboloid. It's just a little bit hard to see because we're kind of on the inside of that paraboloid. And if you're standing at that point and you move in this direction, you'll actually start moving down to the bottom. But if you move basically in further towards the screen, then you're actually going to be traveling up the top of this paraboloid on that other side. So we have to kind of imagine removing this one half so that we can see inside. But the goal here is really just to help us see that these partial derivatives are really telling us about what would happen if we were to move in either one or direction. So imagine that you're actually standing inside of this and that you're standing at this point right here, and depending on whether you move right or you move forward determines whether you move downhill or uphill. In our case, if you move in 1 unit to the right, you're going to be moving downhill. If you move 1 unit forward, you're going to be traveling uphill. Hence the reason we obtain a negative value for dmdc and a positive value for dmdf. Now that kind of depends on where you're standing. Let's say you're on this side of the shell now, and you're standing right here. Well, perhaps a movement of 1 unit in this direction will cause you to move down, and perhaps if you move 1 unit forward, you're actually going to be traveling downhill as well. So it really depends on the point that we've picked, and that's illustrated by the fact that the partial derivatives, both their value depends on the current C position and F position, and here as well on the current C position and the F position. And we see there's some minus signs in here. So on some locations of this surface, there could be a negative slope or a positive slope, depending on which of those locations we're standing at. So this is a little bit more of a complex example because it's hard to kind of imagine what these quantities represent. But once again, what we're saying is if there's an increase in Chrysler loyalists, there tends to be a decrease in the fraction of Mazda loyalists. Oppositely, as the number of Ford loyalists increases, the number of Mazda loyalists increases 7-fold.